Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to demonstrate how electric fields are calculated for a pair of point charges. So in this example, imagine a pair of point charges. I've got one right here, a positively charged particle at 2 microcoulombs. And micro means, by the way, 10 to the minus 6. Over on the right here, I've got a negatively charged particle at 3 microcoulombs, or I'm sorry, negative 3 microcoulombs. Right? And what we're going to do is we're going to try to do a couple things. One, we're going to try to find the electric field halfway between these particles. And then after that, we're going to find the electric field over here, a distance of 50 centimeters to the right of the negative charge. So we're going to do both. So the first thing to do when doing the electric field calculation is draw electric field vectors. So if I pick a point like right here, and again, there's no particle there. That's not a charge. That's just a point in space. If I were to draw the electric field vector due to this positive charge, it would point to the right. I'm going to go ahead and give that a name. I'll call that E1 here for the electric field produced by charge 1. Now, the way I'm getting the field direction, this is right from the definition of the electric field. Basically, you pretend like you put a small positive charge right there. If you did, the force direction would be to the right. So the force direction gives the electric field direction. So E1, field produced by Q1, would be to the right. Its magnitude can be written KQ1 over, I'm going to call that distance x squared. So in this work here, I'm calling that x. So x is going to be 0.5 meters. Right? I'm just going to get rid of that, though, for simplicity's sake. All right, next, all right, this negatively charged particle. If I were to put in a positive charge, again, right at that point, that same point in space, it would feel a pull from the negative charge. Therefore, the force direction would be to the right, and therefore the electric field vector, due to this negative 3 microcoulombs, would be to the right. I'm going to go ahead and call that one E2. And the magnitude of that is going to be KQ2, again, over x squared. Because of the symmetry of the problem here, this point is halfway between them. So x is 50 centimeters. That's good for that distance and that distance. Right? That's why the distance for the bottom of both equations is x. And that's just a consequence of the example I decided to use here. Right? So now, both electric field vectors point to the right. Now they need to be added vectorially. So if we do that, we'd say, all right, the net electric field is equal to E1 plus E2. And I can go ahead and just put these equations in here. So that's going to equal KQ1 over x squared plus KQ2 over another x squared. And if we put numerical values in, and to save myself a little room, I'm going to put NCU, which stands for note consistent units. All right, so the first term is going to be 9 times 10 to the 9th, that's the Coulomb Constant, times Q1, which is going to be 2 times 10 to the minus 6 coulombs, right, over 0.5 meters, and that's being squared, right, plus Coulomb Constant, again, 9 times 10 to the 9th. If I put in the units, it would be Newton meter squared per coulomb squared, times charge 2. Now, charge 2, magnitude is 3 times 10 to the minus 6 coulombs. You do not want to put a negative 3 here. Let me finish out the rest of this, and I'll go back and explain why. And then, again, divided by the same distance, 0.5 meters squared. And this will work out to Newton per coulomb. Now, let's talk plus and minus signs. All right, the plus and minus signs, as far as these charges are concerned, are used to draw the electric field vector directions. When we drew E2, this vector right there, the longer of the two, when we drew that to the right, we have taken the minus sign into account. Right? At this point in this equation, this term, all we want is the magnitude of that term. The directions are right and right. Therefore, both these terms here and the one I've already circled need to be positive. So the directions are already taken into account. We took that minus sign into account when we drew that electric field vector to the right. And this term is just a magnitude. So if we go through and calculate a numerical value, what did I get here? I ended up getting 180 times 10 to the third Newton per Coulomb, or we could write that 180,000 Newton per Coulomb, and the direction is to the right. Another way to write that would be in unit vector form, 180,000 Newton per Coulomb in the plus I direction. If I put a coordinate system somewhere, maybe x, y, something like this. Now, 180,000 Newton per Coulomb, sure, that's a pretty large number. Well, I mean, these are pretty reasonable charges here. 2 microcoulombs doesn't sound like a lot, 10 to the minus 6 coulombs, but it is. It's a reasonable charge. And, you know, charge is more commonly measured in nanocoulombs or 10 to the minus 12 coulombs or so forth. Remember, the charge of an electron is an order of magnitude 10 to the minus 19th coulombs. So anyway, these are pretty substantial charges. So what I'm going to do now is I'm going to take a moment here, clean up this work a little bit, and we're going to try to find the electric field at another point in space. All right, folks, I'm back. I've cleaned my picture up here a little bit, and what I'm going to do is kind of walk through another example here. I picked a point over to the right here, at a distance that I call x equals 0.5 meters to the right of the negative charge. And what we're going to do is we're going to try to calculate the electric field at that point. So just like in the first example, the first thing we want to do is draw electric field vectors for both of these charges. So the first thing we have to decide is, all right, what is the electric field here due to this charge? So what you do is imagine putting a positive charge right here at this dot. This positive charge will repel it, therefore the field direction is to the right. I'm going to go ahead and give that vector a name. I'm going to call it E1. And while I'm at it here, I'm going to go ahead and write down how that is going to be calculated. It's going to equal KQ1 over, now on the bottom we need the distance from here all the way to this point right here. So that is the distance we need for that calculation. I'm going to go ahead and put 1 plus x. Right, and that distance is being squared. Right, now, next $1 million question. We need to know the electric field direction here due to this charge. Right. If I put a positive charge at this dot, this guy will attract it, so the electric field is definitely going to be to the left. Call that one E2. I try to draw that field vector larger than the other one. It's definitely going to be larger because it's more charged and closer. This guy's magnitude is going to be KQ2 over x squared, because x is the distance from this charge to this point. Okay. Now, the net electric field is the vector sum of the two. E1 is positive and it points to the right, so this is going to equal E1. However, E2 points to the left, so it's going to equal E1 minus E2 vectorially. And I'm going to go ahead and write out these equations. KQ1 over 1 plus x squared minus E2, which is equal to KQ2 over x squared. We put numerical values in, and again I'm going to put NCU for note consistent units. All right, the Coulomb constant is 9 times 10 to the 9th times charge 1, which is 2 times 10 to the minus 6 coulombs, over 1 plus x would be 1.5 meters, right? That's being squared, minus 9 times 10 to the 9th times Q2, which is 3 times 10 to the minus 6 coulombs. I'm going to come back and talk about that sign, why that's positive here in just a moment, divided by the distance, which is 0.5 meters squared. Right, and again, why no minus sign? Well, here's why. Because what we're doing is we're adding electric field vectors. We used this minus sign when we drew this field to the left, so the minus sign has been taken into account. Vectorially, because E2 is to the left, that's why that minus sign is there. This is now just a magnitude, which when I carry that along with the equations, that means this is just a magnitude, this just a magnitude. That's why we don't include a minus sign. If you did include a minus sign, by the time you multiply, that would be positive, and it would be inferring that electric field vector is to the right. It's not. So, right? That's why we don't need a minus sign. And again, this thing will come out in Newton per Coulomb. I'm going to go ahead and just pause this for a moment here while I calculate a value. Folks, I'm back. All right, so went ahead and ran numbers here, and what I got out of this is I got minus 100,000 Newton per Coulomb. And the minus sign means left, so there's a couple ways we can write our answer. One way would be 100,000 Newton per Coulomb, and we can use an arrow to give the direction. Or in the language of unit vectors, we could write this as 100,000 Newton per Coulomb in the minus I direction. So, I hope that this video demonstrated reasonably well how to find electric fields in a nice one-dimensional problem. You know, I think my next step here, I'll make a video where we calculate electric fields in 2 dimensions. Have a great day.